Oh, hi there. This is Mrs. Bertrand, and welcome to Hydrates. Hopefully you'll recall from Unit 1 that a hydrate is an ionic compound that contains water molecules that are stuck inside its crystal formation. And these crystals can form from a solution, and as they dry out and most water evaporates, some of that water gets trapped inside, or a dry crystal can just absorb right from the air. A good example of this is down here at the bottom. We've got some calcium chloride trihydrate. So for every 1 calcium chloride, there are 3 water molecules stuck inside its crystal. Another word we need for today is the word anhydrous. Anhydrous means that we have removed the water from our hydrate. So anhydrous means just the dry remaining ionic compound. So the water has now been left. So how would we get rid of the water, you ask? Well, we would heat it. So heating it up can remove the water, and so the leftovers become the anhydrous. And by massing the before and after, the hydrate with the water minus the ionic compound without the water, we can get the mass of the water. So today we're going to be looking at 2 different types of calculations with hydrates. The first is to figure out the percent by mass of water that's in the hydrate, and the second one is to actually figure out how many water molecules are in the hydrate if we aren't aware of that number. So let's start with our percent water. So the first step here is to figure out how much water we have. And as I mentioned before, the mass of our water is just going to be a comparison of our mass of hydrated compound before we heat it up minus the mass of the anhydrous, the dry stuff. And then we're just doing a percent calculation very similar to our percent composition calculations. Instead of a single element on the top of our calculation, we're going to be looking at the whole mass of water compared to the whole mass of the hydrate. And then times 100% will convert it into a percentage. Let's try this on for size. So I've got a 50 gram sample of a hydrate that contains 27.2 grams of barium hydroxide. Calculate the percent by mass of water in the hydrated barium hydroxide. I like to be a bit visual with my particular questions, so I'm going to set this one up with a formula, and then I'm going to chunk which piece is which. So barium hydroxide is a 2+ charge, hydroxide is a 1-, crossing over, reminder that you want to put brackets around a polyatomic. We have some amount of water in the hydrate. It doesn't tell us, so I'm going to use X to represent that value. Now, I've got a 50 gram sample of the hydrate, so this whole thing has a mass of 50 grams. And then I have 27.2 grams of my barium hydroxide. So here's 27.2 grams. So the leftovers, the piece that I'm missing then, the water, is just going to be 50 grams minus 27.2 grams, which leaves us with 22.8 grams. The last piece is just putting it all together. So percent by mass of water is the mass of the water compared to the mass of the whole times 100. And I should get, bringing it to 3 significant digits, 45.6%. Here you'll notice that grams will cancel since they're on top and bottom, so the unit left behind is a percentage. All right, the second piece I need to know is how to figure out the number of waters in a formula. So just like the last example, I had X waters. Now I actually want to figure out what X is. And so I've got a few steps here. The first is to determine the mass of the anhydrous and the water. So we've done step 1 before, where we figured out both pieces, and so we'll start in the same starting place. Step 2, we're going to now figure out the moles of both the anhydrous and the water. So we're going to turn the masses in step 1 into moles in step 2. Again, we always use the same format here. We've done it lots of times. 1 mole equals molar mass. That's our trusty conversion factor. Step 3, we're going to set up a ratio of moles, and then we're going to divide by lowest number. And we've done something similar in our empirical and molecular formula work. It's going to look a little differently because it's going to be a ratio instead of subscripts, but you'll see how this works in just a moment. All right, so here's our example. It's actually the exact same example that we just worked through, only the question is different. So we've got that 50 grams of hydrated barium hydroxide once again. So once again, we've got 27.2 grams of anhydrous, and this time we're finding the number of water molecules in the hydrate. So I've just written out what we've got here. We've got barium hydroxide, X number of waters, that's our goal. What is the number of waters? We have our 50 grams of hydrate, so the whole thing is 50 grams. We've got our 27.2 grams of our anhydrous, and then once again our starting place is going to be the mass of the water, so 50, come on dots, 50 grams minus 27.2 grams, which equals 22.8 grams. So that's the first piece. Now we're going to sort of subdivide our work. So the anhydrous, we're going to work over here and find moles of the anhydrous. So moles of barium hydroxide is 27.2 grams of that, 1 mole over molar mass. And again, we're just working on this half right now. So our molar mass is going to be 1 barium, 2 oxygens, 2 hydrogens for 171.3 grams. Grams will cancel, leaving us with 0.159 moles. Now I'm going to do the same thing on the water side. So I'm going to figure out my waters. Moles of water is going to be 22.8 grams times my 1 mole over molar mass for water is about 18.01 grams, leaving me with about 1.27 moles. So this is all work we've done before. The step 1 is the same as the step 1 in the previous question, and we've done lots of mole to mass relationships. Here's where it's a little bit different. These numbers I've just made are now going to become my ratio. So I'm going to take my 0.159 and put it in front of the compound that it goes with, which is my barium hydroxide. Then I'm going to put my dot in here, and I'm going to put my moles of water in front of water. Now I'm going to divide by the lowest number. The first number should always be my lowest number, FYI, so just so you know. And then again, this will cancel, leaving us with 1. I'm going to put my final answer up here. So 1 barium hydroxide. And then when I divide, whoopsies, totally messed that up. Whoop. Of course, I'm dividing by my lowest number here. Whoops-a-daisies. So when I divide through for that last bit, that's going to leave me with 8 waters. Now, this should always end up being a nice whole number if I give you good values to work with. Every now and again, you might get something that you have to round a little bit, but usually it's pretty close. Unlike the empirical molecular formula where you can multiply to try to get rid of your value, here we should always end up with a whole number. Now, that being said, we are going to do a hydrate lab, and our lab data may be imperfect. So we might get, 7.5 waters or 2.37 waters. It is what it is when it comes to a lab, but in terms of a word problem, usually we're going to just round to a nice whole number. All right, now it's time to practice to make sure you know what you're doing for the next day. Good luck!